Hello, it's Booth here, and today we're going to make an Arduino smart car drive around by itself. We'll start by creating a TinkerCAD circuit to control a motor using the push button, and then replace the push buttons with an Arduino. From there, we'll program a real Arduino smart car to drive around the house and do a few maneuvers. Are you ready? Let's get started. Let's start with the basics, driving motors. I've wired up an example in TinkerCAD to show how this works. It's quite simple. Just some batteries, a push button, and a motor. Pressing the push button completes the circuit and drives the motor. See, this is fun. The pins on an Arduino work a lot like switches, so we can simply hook the motor up to the pins of an Arduino to run. My code is very simple. Just make pin 2 high. Let's run the simulation and you'll see that the motor runs. But see that it only runs at about 51 RPM, which is a lot lower than the 187 RPM we got from the push button. The Arduino pins just don't produce very much power. How do we solve this power problem? We can add an amplifier which will allow our puny Arduino to control much larger amounts of power. TinkerCAD provides the L293D chip, which is an amplifier specifically designed for driving motors. I've already wired up the amplifier, so let's simulate it. The motor still runs when you press the push button, but now the amplifier supplies the power, not the push button. The push button is connected to the enable pin, which then controls the amplifier. This amplifier chip also provides a nice feature. We can control the motor direction using 2 more input pins. I've hooked those input pins up to switches. When one switch is on and the other is off, the motor runs in one direction. When I flip both switches, the motor runs in the other direction. The amplifier chip provides 2 more cool features: the ability to coast and the ability to brake to a stop. Turning both input pins on makes the motor resist turning, acting like brakes. Turning both input pins off turns off power, but lets the motor coast freely. These are very useful features when you're driving a robot around. Let's reintroduce our Arduino to the circuit. We need 3 pins now to drive the amplifier. Pin 5 will connect to the enable pin and act like our push button. Pins 7 and 8 will connect to the input pins, acting like the switches. Now, we just need some code to run this. Our code simply chooses the forward direction by making pin 7 high and pin 8 low. Then, it enables the motor by making pin 5 high. Now our motor is running at full speed. Feel free to tinker on this circuit yourself. Try making different pins high and low and see what happens. It's not really useful to run a motor at full blast all the time. Thankfully, there's a really easy way to control how fast the motor runs, and it's called Pulse Width Modulation, or PWM. Basically, we control the speed of the motor by turning the power on and off really fast. This sends power pulses to the motor to make it move. Here, I've got an example of PWM. I've connected a motor to the L293D amplifier, but this time the enable pin is connected to a 555 oscillator. See how the motor stays around 90 RPM? That's because the power is high for only half the cycle. As a result, it runs about half as fast as before. How about I change the pulses? Flipping this switch makes the power high for only a small part of the cycle, so now the motor only runs at about 20 RPM. Changing the motor speed is as simple as changing the pulse width. Now, back to our Arduino. See the squiggly tilde marking on some of the pins? That means that the pin is capable of producing a PWM output. I chose to connect pin 5 to the enable pin on the amplifier because I can use it as a PWM output. The command for PWM is a little different. Instead of setting pin 5 to high, I'll set pin 5 to a number from 0 to 255. The number 0 represents no power, 255 represents full power, and numbers in between are partial power. So let's set this to 127 for half power and see what happens. You can see that our motor stays at around 80 RPM, and the oscilloscope shows the signal as about half on and half off. How about 192 for 3/4 power? Now, the motor runs at 120 RPM and the signal is mostly on, with only a small dip when it's off. How about 64 for 1/4 power? Now the motor runs at 40 RPM, and the signal only has a small spike when the power is applied. Feel free to tinker on this to play with different power values here. So far, we've been driving just one motor. My Arduino robot car has 2 sets of motors, and I want to be able to run all of them. Thankfully, this one amplifier chip can run both sets of motors. All I need to do is wire up the other side of the chip and program the Arduino. TinkerCAD is great in so many ways. One awesome feature is that it translates the blocks code into Arduino C++ code. All we have to do is select blocks plus text from the drop-down and we get the fully functional C++ code. I can take this C++ code and upload it to my Arduino robot car. This TinkerCAD example is wired exactly the same way as my Arduino robot car, so all I have to do is copy the C++ code from TinkerCAD, paste it into my Arduino IDE, and click Upload. Now, my Arduino robot car is running just like the TinkerCAD example. You should be able to do the same thing with many different Arduino robot cars, although you might have to change the pin numbers to match how your car is wired. So far we explored how you can drive motors from an Arduino, but that's not the same thing as driving a robot car. Driving a robot car is a finely choreographed dance of timed instructions to move forward, backward, left, and right, and stop. All we've done so far is make motors turn, and even then, they were virtual motors. To make my robot car move in useful ways, we need to start turning commands to run motors into a set of timed instructions for my robot to do specific maneuvers. Let's understand the problem by taking a closer look at my robot car. I've taken the top plate off to show the drivetrain. You can see there are 4 motors driving 4 wheels, and I've got a big amplifier chip and circuitry in the middle. This is just like our dual motor TinkerCAD setup, just with some more circuitry and 2 more motors. Driving forward is easy. All we need to do is drive all 4 motors in the same direction toward the front of the robot. Reverse is easy too. We drive all 4 motors toward the back of the robot. Steering is a bit trickier. The wheels can't turn left or right, so normal car steering isn't an option. We can drive the left and right sides with different amounts of power, so tank drive is a good option here. If we want to turn left, we just give extra power to the right side, or take some power away from the left side. If we want to turn right, we do the opposite. Additionally, one nice feature of a tank drive is that the car can spin in place without moving any distance at all. Let's get to making our drive code. We're going to create code for moving forward, backward, left, right, and stopping, and save that code into different files for reference later. Later, we'll use these pieces of code to drive our robot in interesting ways. We already have some code from our dual motor TinkerCAD example. We saw that it's good code for driving forward, so let's put it in a safe place. I'm saving this code file as drive forward. I want to drive backward next, but I need to remember what all these commands are for. Let's take a second look at our code to figure this out. The pin mode commands work just fine and don't need any changes, since I'll only be using these pins as outputs anyway. The first 3 commands control pins 7, 8, and 5, which control the left motors on my robot. Let me add a comment to remind me that these commands control the left motors. The second 3 commands control pins 9, 11, and 6, which control the right motors on my robot. Let's just add another comment. I'm also going to add some space between our left motor commands, our right motor commands, and that delay command at the end. Doing this groups code into logical chunks, just like when you're writing paragraphs in an essay. This helps to remind you of which chunks of code go together. Now that we remembered what our code does, let's make it drive backwards. First, I'll save this as drive backward, since that's my goal with this code file. Next, I remember that the amplifier input pins control the direction, and the enable pins control the power. To reverse direction, we just need to reverse the amplifier input pins. Let's do that. Our amplifier input pins are connected to the Arduino pins 7 and 8 for the left side, and 9 and 11 for the right side. For those pins, I just turn high into low and low into high. Then, let's upload our code and see what happens. Success! Our wheels drive backward. How about turning left? Let's go back to our drive forward file and save it as turn left. Next, I'll just take the left motors and reverse the amplifier input pins. See? Now it spins left. Let's turn right in a similar way. We just save the file as turn right and reverse the direction of the right motors. It's also nice to be able to stop. The amplifier chip gives us two options, brake and coast. Let's make some brake code first. We'll go back to our drive forward file and save it as brake. Next, I make all the amplifier input pins high, which will make the motors brake. Let's also save this file again as coast and make all the amplifier input pins go low, which will let the motors spin freely. We've got the code now to go and move in one direction forever, or turn in place forever, or to stop forever. What we really want to do is move for a bit, turn for a bit, move for a bit, turn for a bit, move for a bit, and then stop. We can do this by running some move code, then the delay command, and then some more move code. Now that I've got all the code pieces I need, I put them together to move along a complex path. As you can see, I just cycled between code to move, code to delay, and code to stop. I had to use a lot of trial and error to get my robot to move along a complex path. I even had to add comments so I could remember where I was on the path. As you can see, it works, but not super well. It'll require quite a bit more tuning to turn at precisely 90-degree angles and to travel precise distances. I could make this a lot better using encoders to track how far each wheel turns. It would be even better to add an MPU 6050 6-axis motion tracking device to track our precise position and direction using its 3-axis gyroscope and 3-axis accelerometer. Go ahead and put the code on your robot and see if you can do better. The code is in the link in the description. What did we just accomplish? We built up our knowledge using TinkerCAD circuits and then applied that knowledge to an Arduino robot car. We figured out the code to drive forward, backward, turn left and right, and to brake and to coast. Then we coded an Arduino robot car to follow a path using these ideas. Thank you for watching my video. Please like and comment and subscribe for more videos like this. Just so you know, the TinkerCAD circuits and the code are all in the description below. Thank you and have a great day.